All right, so let's see if we can get through this whole part, right? I don't know, we'll see. So we need to pick up where we left off. That, by anybody's account, that would make 3 assignment slides, so I don't know, we'll just see. So we were talking about using solution concentration as a conversion factor. So in this case, basically the big M, remember, is molarity. So actually here in a minute, we're going to unpack that M as 0.432 moles of C2H12O6 per 1 liter of solution. And I have it kind of diagrammed on the next slide, but basically we're after question mark grams of glucose, okay, is in 125 milliliters of solution. Okay, and actually you're going to see here in a minute there are just kind of a couple steps you need to do to go in between them. But one of them is to unpack molarity, 0.432 moles of C6H12O6 per 1 liter of solution. That's actually going to be one of our conversion factors. So here we go, kind of the diagram. So we're going to use molarity as a conversion factor, but we can't use it with milliliters, so we have to convert milliliters to liters, and of course we've done that a lot in here, using the 1 liter is equal to 1,000 milliliters. And then we know we can use the molarity to get from liters of solution to moles of solution. Okay? So from the molarity, we'll get from liters of solution to moles of solution, and then we're after grams of glucose, so we can get from moles of glucose to grams of glucose using its molar mass. So that's exactly how we're going to work this. the molar mass of C6H12O6. So here we go. It's all in one problem, and it kind of wraps around. I was talking to one of y'all, and it's almost like you should take these and turn the paper landscape so you can get them all to fit in one line. So if we make our first term the volume of solution, 125 milliliters solution over 1, convert milliliters to liters by this term, 1 liter of solution over 1,000 milliliters of solution, milliliters of solution cancel. Then the third term, we're ready to introduce molarity. So we're going to use the unflipped version of molarity. 0.432 moles of glucose per 1 liter of solution. That's your molarity term. Now, if you kind of see what units we have finally gone from volume to moles. All right, so now we're ready to go to grams using the molar mass of C6H12O6, and I didn't show that calculation, did I? Hopefully I did it somewhere else in your notes. So you would need to show this calculation. It's 180.16 grams of glucose per mole of glucose. Yep. And I remember this every year I get to this point, like I should have done that molar mass somewhere. So now moles cancel, we're left with grams. It looks like we need to round according to 3 significant figures. So I got 9.73 grams. Of glucose. All sorts of possible problems with solution concentration. All right. Another one. Okay, a solution of acetic acid, it gives the weight percent of acetic acid in acetic acid solution. So, and then also gives the density of the solution, 1.07 grams of solution per milliliter solution. And what is the molarity of this solution? Okay. There's a few ways to work this, okay, but one of the things you're going to see me do right off the bat is to unpack that weight percent and that density. When we worked with weight percents before, it's important that you're explicit about grams of what over grams of what. So 76.0% acetic acid means 76.0 grams of acetic acid, which is CH3COOH. You can just put it AA if you want, in 100 grams of solution. I say rarely, sometimes I give you information you don't need to use. You need to use both the weight percent and the density. So remember then, whenever we're talking about the density of a solution, that actually means the 1.07 G/ml means 1.07 grams of the whole solution per milliliter of the solution. And then sometimes what we've done when we doodle is we put like question mark, that's our target. Our target is molarity. So our target is what? Moles of CH3COOH, or CHU, over liter of solution. So that's our goal. Okay, and so can you kind of start to see these puzzle pieces? So I've got, if I like flip this one and bump it up against the top term, do you see where units of grams of solution cancel? Yeah. And so that's kind of like if you play puzzle, you're kind of like, you just move things around. And then I'm close. If I do that, I'm going to have units of grams of acetic acid per milliliter of solution. And I'm close. But I need to fix the milliliters into liters, and then I also need to fix grams into moles using the molar mass of acetic acid. So let's go ahead and knock out the molar mass of acetic acid. You take 2 times the decimal number for carbon. You guys already have this? Okay, good. So the molar mass of acetic acid is 60.05 grams per mole. All right, so let's work this. And in this case, I'm going to string them up. You could also do it on like a choose your basis. And that's actually in the homework problem how I say to go about it. But here we go. Solution, no pun intended. Okay, if we start with the weight percent, keeping an eye on our units. So the weight percent is 76.0 grams of acetic acid, CH3COOH, per 100 grams of solution. Then, like I said, looking at the units, we want grams of solution to cancel, so we're going to use what? The flipped version of the density. Okay. Oops. I guess my next term isn't doing that. Look what my next term's doing. It's actually introducing the molar mass. What molar mass does for us is it gets units instead of grams of acetic acid. Okay, it gets units of moles of acetic acid in the top. So this is the flipped version of the molar mass. So unit-wise, we have moles of acetic acid per 100 grams of solution, and we want moles of acetic acid per liter of solution. So now we go with density. So that third term there is density. So now grams of solution cancel, and we're left with moles of acetic acid per milliliter of solution. And we're close. So now we can go ahead and fix the milliliters if we introduce what, 1,000 milliliters over 1 liter? 1,000 milliliters of solution over 1 liter solution. Now it's looking pretty good. Grams have canceled. Grams of acetic acid have canceled. Also grams of solution have canceled. Milliliters of solution have canceled. We're left with moles of acetic acid over milliliters of solution. Looks like 3 significant figures. Remember that 100, there's no uncertainty introduced because that was by definition 100 grams of solution. So we get 13.5 moles of acetic acid per liter of solution, more affectionately written just with a capital N. So 13.5 molar acetic acid. And that's it.
Moles of choo-choo.
That's right. Moles per liter choo-choo.
Train.
Okay, so we'll take a real quick look. So these are what I gave to the students last year. So for 35A, basically they give you the molarity of the glucose, and they give you the volume, and they want to know what sort of mass needs to be dissolved. So you're going to go from the volume, convert it to liters, and then you're going to use molarity. That's the 0.350 molar to get from liters to moles, and then you're going to use the molar mass to get from moles to grams. And then the other one I think is similar. The other one, you have an extra step because the solute being dissolved, methanol, is actually a liquid. So once you get to grams, one last step, they're wanting density, or excuse me, they're wanting volume. And so you can use the density of the methanol that's given to get from grams to volume, milliliters. And then for 36A, kind of similar to 35B. And 36B, kind of similar. So there's my hints. Like I said, I'm going to post these right after class. So the next couple kind of go together. Basically, you have two solutions, and I identified them as A and B. A is 46% sucrose. B is 1.50 molar sucrose. And you're supposed to say which one's more concentrated. So definitely different ways to skin this cat. What I did basically is find the molarity of the 46% by weight solution and then compare it to the 1.50. And this is where I did like a basis. I said consider 100 grams of solution. If you have 100 grams of solution, then you have 46 grams of sucrose. From that 46 grams of sucrose, you can use the molar mass to knock out moles. Then to find the molarity, you need to know what volume that mass is floating around in. They do give you the density of the solution. So actually use 100 grams of solution, which was your basis. The fact that the density was given to get to milliliters and then ultimately to liters. Once you have liters, you have moles and liters, you can get molarity. There might be an easier way to do this one. You can get to molarity by dividing the moles of sucrose in that solution A by the volume you got from the density. And then you compare it to 1.50. I understand it's just a 50-50 chance of getting it right one way or the other, but you have to explain your reasoning. So that's what I would do. And the last one, very similar to the previous one. I went ahead and brought in a screenshot when it says, it refers to example 4.8. This is example 4.8. So you're comparing it basically to a solution has a molarity of 1.71. All right. On to another type of problem. So this is oftentimes done in the lab, and it's hard for me to explain why this is. But basically, say you have a solid that you want to have a very diluted solution of that solid. Okay, so there's my volumetric flask, okay? I go ahead and I make up one solution, and actually this is going to be called my stock solution. Okay? But I want it very diluted. So then basically I use a pipette. You guys have used pipettes, right? I use a pipette. I grab an empty volumetric flask, another volumetric flask, and I pipette a small amount of my stock solution into, I'll just call this diluted solution. I pipette a small amount, let's go ahead and call it 10.00 milliliters, because you get different pipettes, but that's a good pipette. I transfer it over, put it in the bottom here, and then dilute this back up with water. Okay, now I have a diluted solution from my stock solution. The reason you would want to do this is actually called just a dilution. Sometimes there's a serial dilution. So you make this one up and then you transfer it over. You make another one up. You transfer a small aliquot to another container. Okay, that would be a serial dilution. The reason you would want to do that is, let's just say if I go over here and I do this several times, taking a 10 milliliter aliquot, transferring it to a new volumetric flask and diluting with water. Over here, I have a very, very diluted, okay? I'll just put V for very diluted. I could not, I'll put a question mark here, I could not take a certain amount of mass of my analyte and just a hair's bit of analyte and dilute it up with any sort of precision, with any sort of accuracy. It just would not work. Okay? We get accuracy with this serial dilution that we don't get if you just go straight for the diluted stuff. This brings with it, you're like, hey, but you're doing more procedures, you know, there'd be uncertainty in all of your, yes, but it just, that doesn't work. Some cases you don't have a balance that can actually read that small of a gnat's eyebrow of material. So that's why you'd want to do it. So let's do just a simple dilution problem. And I think this one needs a picture. I like pictures. And my volumetric flasks look terribly ugly, but there you go. Okay. So this is actually my stock solution on the left, and this is actually going to be my diluted solution on the right. Okay. And notice that it says 25 milliliters of the stock, which is, and this is where I start to label things, the stock is 0.160 molar. The analyte running around in there is calcium chloride, CaCl2. We'll talk more about how you name that. Running around in my stock solution. And it says that 25.0 milliliters, so an aliquot. We got pipettes in the lab that actually are that volume. 25.0 milliliters are transferred, okay, into a new volumetric flask, and this volumetric flask has a capacity of 125 milliliters. Now, usually it'll say 125.0 milliliters, but we'll just go with that. Oh, yeah, it does say. Okay, so 125.0 milliliters. All right. So, where's the question? There's no question yet. Oh, it's coming. So the question, I hope you got that picture. The question is, what is the molarity of that diluted solution? So I think the best way to go about this, I wish I hadn't, I don't think I can make it come back. Oh, yes, I can. Watch this. I thought it would. Nope. Oh, maybe it did. Okay, yeah. The best way, I think, to go about this would be to, that's not the right picture. This one. Is to, you're going to see me do it stepwise. Basically, my first step is to come up with what is the moles, what are the moles of calcium chloride transferred? CaCl2 transferred. We can do that because we have a volume and molarity. We have volume and molarity. So we get the moles transferred, and then all we got to do is divide that moles, part number 2, is divide the moles by its new volume, which is 125 milliliters. And then you're done. That's the molarity of your diluted solution. So here we go. Maybe. So moles in that aliquot that you transferred, we take the volume, which is 25.0 milliliters. That's going to be our first term, 25.0 milliliters over 1. And then, of course, molarity, we're going to unpack that 0.160. That's moles per liter, so we have to stick in a conversion here. So we put 1 liter over 1,000 milliliters is our second term. And then we have liters of solution. Now we're ready for molarity. So then we can put 0.160 moles of CaCl2 over 1 liter of solution. And this is all just to find the moles of calcium chloride in your pipette. Okay, rounded to 3 significant figures. I got 0.00400. Okay, so yeah, don't forget that, how that works. There's your 3 sig figs. All right, so then all we got to do is divide those moles transferred by its new volume. Okay, so the new volume was a volumetric flask that had a capacity of 125.0 milliliters. So if we were to look at our units, we don't quite have molarity yet, so we need moles per liters. So the next term fixes that. So if we put 1,000 milliliters of solution over 1 liter of solution, then by golly, we have moles per liter of solution, which is great. Looks like we're again only allowed 3 significant figures. Okay, so 3 significant figures is 0.0320. And that would be units of moles of calcium chloride per liter of solution, or simply 0.032 molar CaCl2. That's it, that's just dilution. And this is a good type of chemistry problem where it never hurts to look back at it and say, does that make sense? Now, if you come up with a molarity that's more concentrated than your stock solution, you did something wrong, which it happens. I realize that there are other ways, and I even hesitate to bring this up. Oh, what the heck. If you go on and take Gen Chem 2, we actually will let you use this one. If you don't know what that means, and I think Petrucci talks about it, if you don't know what that means, that's fine, because you can't use it in Chem 1. But if you do know what that means, you can use it in Chem 2. All right. So here is this is just kind of a still image of kind of what you saw. The stock solution is in the beaker, and the waiting volumetric flask is where the diluted solution is being prepared. So an aliquot is transferred and then brought up to volume, and then don't forget to mix it. So down below, the caption actually kind of talks you through what is the concentration of the stock solution, what's the volume of the aliquot that was transferred, what is the volume of the volumetric flask it was transferred to, and then what is the resulting concentration of the diluted solution. Okay, and actually this problem right here goes along with the little video we saw. Okay, so remember it was 2 mils, there's 2 mils, okay? Transferred to a 500 ml volumetric flask, transferred to a 500 ml volume, you know what I'm saying. This one's a little bit different. So again, I'll go ahead and this, I guess it wouldn't have to be volumetric flask, but with regard to the stock solution here, we are given not a lot of information. Okay, yep, we got a big honkin' 500 ml volumetric flask over here. Okay, the aliquot that was transferred was 2.00 milliliters of stock to get to the diluted. Okay, and in this case, the molarity of the diluted solution was given. So this is why I like diagrams sometimes, because the resulting solution is, so over here under diluted, I'm going to put 1.60 times 10 to the negative fourth molar K2 CR2O7. Okay. I don't have the question yet. You guys have the question. So the question is, what is the molarity of the stock solution? So over here, my stock solution, I'm going to put question mark molarity. So in this case, it's a little bit different. Notice that I know more about my diluted than I do my stock. So do you see where from the diluted solution we can use the volume and the molarity to get to moles? We can use these to get to moles. Okay, that's actually going to be my first step. Get to moles from that information. And then once I have moles, all I have to do is divide the moles by the transfer volume. Because where did all those moles come from? From 2 milliliters of my stock. Okay, so my second step is divided by, take the moles and divide it by this volume. I'll just put T for transfer volume. It's kind of backtracking to what the molar concentration of the stock must have been. And when I do this, I want to say when I do this, I like label my steps. Okay, so here's the first step. Moles of K2CR2O7 in your diluted solution. So there was 500 milliliters, so 500 milliliters of solution. Sometimes if I label them like this, then I don't have to say of the diluted solution, because sometimes you have two solutions. You have diluted and stock. So if this one is moles of analyte in, oh, it doesn't say. It should be stock. Anyway, so of course we're going to use the molarity, but we can't use molarity with milliliters, so I'll use it with liters. So the next term is going to be the 1 liter over 1,000 milliliters. And then the next term is going to be the molarity. So that we're going to unpack that 1.60 times 10 to the negative fourth m, and that means 1.60 times 10 to the minus fourth moles of K2CR2O7 per 1 liter of solution. And then milliliters of solution cancel, liters of solution cancel, and we're left with units of moles, which is what we want to know. So yeah, I probably would, I guess it did say the diluted solution in a sense. Okay, so round it to 3 significant figures. 8.00 times 10 to the minus fifth moles of K2CR2O7 was in that 2 milliliters aliquot. And then the last step is to take those moles and divide it by the aliquot, transfer aliquot. So 8.00 times 10 to the minus fifth moles of K2CR2O7 divided by 2.00 milliliters of solution. That would be stock solution now. So molarity, of course, is moles per liter, not moles per milliliter. So we need to introduce 1,000 milliliters of solution over 1 liter of solution to get our units right. So rounding it to 3 significant figures, I get 0.0400 moles of K2CR2O7 per liter of solution, otherwise called 0.0400 molar K2CR2O7. Here's one that you guys might be wondering. So I am definitely about labeling. So can you go straight to this answer from here? And I would say the answer is yes. Do you have to put these units explicitly like that? Probably not. All right. Another assignment slide. Dun, dun, dun. We kind of need to be getting down the road here because we've got, on Thursday, your lab, it's a titration lab, which is aqueous solution, and then we combined it with stoichiometry. So we kind of getting ready for that. So taking a look at these. They look like this. So I have little pictures here of the two, my stock is in a beaker, and the thing that's going to be diluted is an Erlenmeyer flask, or excuse me, volumetric flask. And so if you read this, I'll just kind of show you what the picture looks like. Or no, I guess that is the picture. But in this case, this is like the first problem we did, where you know the molar concentration of the stock, you know the transfer volume was 10 milliliters, and you know that the volume it was diluted up to was 250.0 milliliters, and you're supposed to get to the concentration. So get the moles that were transferred using the molarity and the volume, and divide those moles by the new diluted volume. And the other one? Their volume wasn't given. We didn't do one of these yet today. But what do you know the most about? Well, it gives you the concentration of your diluted and the volume of your diluted. So we can get to moles there, right? Okay. It gives you the molarity of your stock. So we can get moles from volume and molarity. Okay. And then once we have moles, we can use molarity of the stock to get to volume. All right, so there's your hints for that one. Next one, see the pictures are just so helpful. So this is like one that we did, I think one that we just did, where you know the diluted volume and concentration, you know the transfer aliquot. So we can get moles of, in this case, HCl transferred from volume and molarity. Then we can actually divide those moles by the transfer volume. All right, last but not least, given 2 liters of, So this one is where basically answer the question, how much of your, okay, so this is your stock. I know it's your stock because it's more concentrated, 0.496 molar versus 0.175 molar. So you're supposed to say, how can we take some of this stock and make that volume of KCl of that, given that molarity? So it's very similar to the previous problem. All right, so this is just kind of one tack-on little topic. So we're going to talk more about two different types of compounds, ionic compounds versus molecular compounds. But ionic compounds are great at dissolving in water. And you know when we see the AQ, well, that's not a good example. But anyway, they're great at dissolving in water. So for instance, salt, regular old table salt, is of course NaCl. When it dissolves in water, it breaks into the sodium cation and the chloride anion. We'll be talking more about that. Calcium nitrate, the formula for calcium nitrate is, and even if you don't know its name or kind of forget how this whole thing works, do you see where when it breaks apart, okay, you get 1 calcium and you get 2 nitrates. Now, if you haven't been exposed to it lately or how that all goes, if you don't know that this is NO3 with a -1 charge, that's okay. my point, the most important point here is the 2. And actually, the one thing I want you to focus on is if I have 1 mole of the calcium nitrate, 1 mole, this is how the problems are going to go. Notice I get 1 mole of Ca plus 2, and I get 2 moles of NO3. Okay? Oops, sorry. 2 moles of that. That's the big thing there. One more. Oh yeah, I guess that's no more examples. All right. So here's how this sort of problem would go. What is the concentration of the nitrate ion? So I'll just find the nitrate ion, find the NO3, write question mark, concentration underneath that. What is that concentration if the concentration of the salt is 0.230 molar? And if you're like me, you'll be like, well, it's twice as much, right? Looks like 0.460 molar, and you're right. But we need to be able to use basically kind of amounts to a stoichiometric ratio to get there. Okay. If you consider what 0.230 molar means, it means 0.230 moles of the salt, calcium nitrate, per 1 liter of solution. Then we recognize that as it falls apart, you get 2 moles of NO3 for every 1 mole of CaNO3 quantity 2. And that's it. You still come up with 0.460, so you're totally right. You are totally right. But you need to be able to kind of, this might be a good example where you come up with the right answer and then you look back at how I can come up with a ratio to get the right answer. So that's it. Actually, the problems I have for you are clear in Chapter 5. So we kind of skip a little bit, but it's definitely solution concentration. And we'll be talking more about the whole ion thing. So here are the problems, and here's what they look like. And I did the one for you. Maybe. Oh, come on. Well, I'll find them and push them out there. How's that? Oh, wait a minute. No, I know where they are. I got it. I was in the wrong folder. I knew I did them. Okay, so 7 and 8 look like this. And so I went ahead and did 7D for you. But basically, they tell you, oh, this is one of the things I need to mention because I forget this sometimes. This actually is important in chemistry. Anytime you see brackets, brackets means molarity. Okay? So the brackets, K means what's the molarity, or K plus means what's the molarity of that K plus or the potassium ion. Okay? So actually the first one, okay, you're going to want to show me that with the ratio. You do have, if you have 0.238 molar KNO3, since there's like a 1K for every KNO3, you have 0.238 molar K plus. But you're going to have to show that one little ratio, okay? So I went ahead and did D. So D in the formula for this salt, notice that you have 3 NAs for every formula unit. So that's what I wrote down here, 3 moles of Na for every 1 mole of the salt. Okay, so that's how you would do that. Okay? All right, thanks, that's it.
Those aren't so bad.
No.